Hello everyone, this is Professor DePaulo. Welcome you to this walkthrough video for the Practice Lab Psych 220. And I'm going to be going briefly over how to do the Practice Lab as requested. So first you're going to open the Porto and you're going to upload the SPSS Lab Practice save file like I have here open. And once you have this opened, you have to upload it to Porto first if you haven't uploaded it yet. We're going to have these columns set up like this, and we're going to start on the lab. So the first question is provide the means and the standard deviations for depression 1, stress, and income. So we're going to do this a specific way. There's multiple ways to do this question. We're going to do this analyze, descriptives. And the reason why we're doing this is because we're going to set up z-scores for question 2. You're going to put the 3 continuous variables here in the variable list, and you're going to check off save standardized values as variables. And then this is going to make the z-scores, this checkbox. And then you're going to hit OK. And these are our descriptive stats, right? And if we go to the data, we can see the z-scores. We're going to need this for question 2. So this knocks out question 1 and gives you part of the answer to question 2. Now for question 2, it's asking about making histograms. So there's also multiple ways to do that. I'm going to do analyze, descriptives, explore, put the 3 continuous variables in this dependent list. Under statistics, we want to have descriptives checked off. We don't actually need this, but we can have this to look at the skewness. Under plots, we want to have histogram. We don't want a box plot, right? We don't want any of this stuff. We just want histogram. Then you're going to leave both here. You're going to hit OK. And the reason why you want to leave both is because you get the skewness coefficients here. So depression 1, the skewness coefficient is negative. So that means it's slightly negatively skewed. Normal would be 0 skewness. Stress, a little bit more negatively skewed. And then income, greatly positively skewed. The bigger number, the more skew. And you could tell that by looking at the histograms here. Here's depression 1. It's negatively skewed, although you have this data point here that could make it more normal. So I would accept normal or negatively skewed. For the second one, stress, you have much more negative skewness here. And then for income, we have the opposite. We have a very highly positively skewed due to this outlier. Okay, so those are our histograms. I just made a duplicate copy of them. They're not different analyses. And then we want to look for outliers. So we want anything that's greater than 2.58 and anything that's less than negative 2.58. And so we can just scan these columns and look for the outlier. So here's an outlier. This is less than or more extreme than negative 2.58. So that's case 17 for depression. We see the same thing for case 17 for stress, also an outlier. And for income, the outlier is down here at case 24. So I'm just scanning these columns for large values that are greater than positive 2.58 or more negative than negative 2.58. So that's question 2. Question 3, correlations between stress, depression, and income. So you could do these 2 at a time, or you could do them all at once. I'm going to do them all at once. But you just have to be careful when you do them all at once, you're looking at the right thing. So analyze, correlate, bivariate. So we want depression 1 again, stress and income. We want to make sure we have Pearson, two-tailed, and check off all 3 of these bottom ones. And hit OK. And here's my correlations. As you can see here, depression and income, the correlation is negative 0.102. That is not significant. And the reason it's not significant is because the significant value is not less than 0.05. Right? So depression and income, negative 0.102, not significant. Depression and stress, 0.264, also not significant, 0.202, not less than 0.05. And then stress and income, negative 0.038, also not significant, 0.859. So these are relatively small correlations, and they're all not significant. So they're not significantly different than 0. So that's question 3. So there'd be no asterisk next to either. Now, in SPSS, if there's significance, you're going to see an asterisk. SPSS will put an asterisk next to these things. But it doesn't do it here because these are not significant. So let's look at the next one. Stress predict depression. So when you see the word predict, it's regression. So the stress as the independent variable predict depression. Let's take a look. Analyze regression linear. Independent variable stress. Predicted dependent variable is depression 1. And then just hit OK. And then we're going to look at the model here. So if we're looking for significance, we're going to look at the ANOVA, where it says regression. F is 1.726. Sig is 0.202. So you're going to want to report both of these. You're going to put F is 1.726, and the sig is the p-value, right? So p is equals 0.202. And since 0.202 is not less than 0.05, we fail to reject the null, and this model is not significant. So stress does not significantly predict depression because this value is not less than 0.05. Now, could you use this coefficient box? You could. If you want to give me the stress coefficient and the t-value here, 1.314, you can give me that too, instead of the F. So either one will work, the F or the T. You see the significance value is the same because these are the same results. All you have to do here for T is you square this. If you square T here, you're going to get 1.726. And the reason that's the case is because there's only one predictor. If there's more than one predictor, you're going to want to look at the ANOVA because that's going to tell you all the predictors. And then you could look at each individual predictor down here. But since we only have one predictor, they're the same really. So you can either report the F and the P, or you can report the T or the P. They're both the same answer basically. What else do we need? What percent of variance does stress predict? Well, that is the R squared value here. So this is 0.070. And if we multiply by 100 to get percentage, it's 7%. So stress predicts 7% of the variability in depression. Write the equation of the regression line. So that's also given here in the coefficient box. So you're going to look at the unstandardized coefficients. So the regression line would be 0.216 times stress plus 43.196. So 0.216 times stress, which is our x, right? Our x is stress here. 0.216 times stress plus the y-intercept, which is 43.196, is the regression line. Predict a value of 85. All you have to do is put in 85 here. So there'd be 0.216 times 85 for stress, 0.216 times 85 plus 43.196 would be your predicted value for a stress score of 85. Number 5, do illegal drug users differ from non-users? Well, illegal drug users have two categories. They're either drug users or they're not drug users. So income is continuous and drugs is categorical. It's discrete, has two categories. So we have a t-test. Now, drug users and non-drug users are different groups, right? You can't have both a drug user and a non-drug user. It's impossible. So you have two different groups. They're independent of each other. So we want independent groups t-test. So analyze, compare means, independent samples t-test. We're going to do the grouping variable for drug. Now, drug is 1 and 0, because if you look at the data here, drug is categorized as 1 for drug user and 0 for non-drug user. So you have to put 0 and 1 in the box for grouping variable. So let's go back to the output that we're looking at, the menu here. Right, so drug has to be defined groups, has to be 0 and 1. Not 10, 0 and 1. Income is our dependent variable, so we put that up here. You can check the homogeneity of variance test if you want. Estimate effect size, uncheck that. You don't need effect size for this. Hit OK. We're going to go with equal variances assumed for these tests because they're all meeting the criteria for equal variances assumed. So look at equal variance assumed. Here's your T, 1.929. And we're looking at, is there a difference between drug users and non-drug users in income? And so since we're looking for difference, we're looking for a non-directional test. So we want the two-sided P because this is a non-directional hypothesis. So T is 1.929 and P is 0.066. That is not significant. It's not less than 0.05. Therefore, there is no difference between drug users and non-drug users in terms of income. No significant difference. It's close, but it's not good enough, right? And the reason why it's not significant is because the sample is small, 25 people. I mean, the mean difference is large. People that don't use drugs make a lot more money than people using drugs. But since the sample is very small, this is underpowered, and therefore we can't reject the null. So that would be no, there's no difference. You'd give me the t value, and you give me the p value. Does education have an effect on salary? Let's look at it. Education has multiple categories, more than 2 categories, so therefore we use ANOVA. So compare means and proportions, one-way ANOVA. We're doing income again. And the factor is the independent variable, so therefore that's going to be schooling. We don't need effect size for this. We're going to also check off post hoc Tukey. Just in case, if our ANOVA is significant, we're going to look at the Tukey test. So just check it off just to have it so you don't have to go back and do it again. If the ANOVA is not significant, you will not look at the Tukey tests. Because when the ANOVA is not significant, there's no difference among the groups. So there's no point looking at post hoc tests. So only if the ANOVA is significant do we look at the Tukey test. Leave the rest of this alone. Hit OK. Here's our ANOVA. We're looking at F, which is over 7. We're looking at the p-value, which is less than 0.001. So this is definitely significant. That means all the groups are not the same. Now, where are the differences? Wherever you see an asterisk here is a difference, significant difference. So group 1 and 5 are different. Group 2 and 5 are different. Group 3 and 5 are different. Everything else is the same. No, there's no significant difference with anything else. So the only groups that are different are groups 1 and 5, 2 and 5, and 3 and 5. And if you look at the key for the practice lab, you can tell which those groups are. So one is high school. So high school and PhD are different. College and PhD is different in salary. And college degree and PhD is different. And there's no difference between master's degree and PhD. Well, that makes sense. I mean, you have more education, you get a better job, you make more money. But obviously no difference between master's and PhD because, once you have a master's degree, you pretty much are fully qualified for whatever job you're doing, except maybe working at a university. So you can see the different groups from looking at this key of the data points of the data in the file we're looking at. Let's go back to this. So you want to say group 1 and 5 are different, 2 and 5. So 1 and 5 is high school and PhD is different. Some college and PhD is different, and a college degree and PhD is different in terms of salary. And then between master's and PhD, no difference, right? Now, 1 and 5 is the same as 5 and 1. So there are duplicate values in here because 1 and 5 and 5 and 1 are the same comparison. So just count them once. And that's number 4. I mean, not number 4. That's number 6. Number 7. We're comparing the sample income to the average annual income of people in the U.S. at 40,000. So since we're comparing a sample mean to a population mean, we are doing a one sample t-test. So analyze, compare means, one sample t-test. We're comparing to 40. We're comparing sample income to 40. We don't need effect size. Hit OK. Here's our t-value down here, 0.934, not very impressive. We're asking, is it different than 40? We're not asking if it's greater than 40 or less than 40. We're saying, is it different than 40? Is the sample income different than 40? That's a two-tailed test. It's a non-directional hypothesis. We want a two-sided p, 0.360. That's not less than 0.05. So we fail to reject the null here. And if we fail to reject the null, we have to conclude that the sample salary is not significantly different than 40,000. Here's our t-value, and here's our two-sided p-value. You're going to report those. The last one, does CBT have an effect on depression? Well, if you look at the key here, depression 1 is depression before CBT. CBT is cognitive behavioral therapy. It's a very common therapeutic technique to treat depression. And depression 2 is depression scores after CBT. So you have a before and after phenomenon here. And whenever you have before and after, you have a correlated groups t-test, or what SPSS calls the paired samples t-test. So we're going to look at paired samples, which is analyze, compare means, paired samples t. We're going to look at depression 1 and depression 2 together. Make sure they're in the same row. We don't need effect size for this assignment again. Hit OK. Where it says paired samples t-test, we're looking for t, 2.231, and we are looking for two-sided p because we're looking for difference again. Not a direction, but just a difference. So two-sided p is 0.035. That is less than 0.05, so that is significant. So we conclude that CBT for depression is effective because it lowers depression. It changes, technically changes depression level, right? You could tell by the means that it lowers it, right? But we're testing a two-tailed hypothesis. And T is 2.231, P is 0.035. So CBT does have an effect on treating depression. And that's problem 8. And then you're done. Very simple. 8 problems, goes through each of the labs that we went through during the semester. And hopefully you have some idea of how to analyze basic data. It's obviously not going to be that you took the exam and you know it and you can go out and analyze any kind of data set, but it's one step in the direction of being able to analyze basic data. The more you do it, the better you get at it. The more you use SPSS, the better you'll get at it. And you'll need it in graduate school, and you'll need it on the job. On many jobs, almost every job uses data. Whether they use Excel, SPSS, they use R, they use Systat, they use SAS, whatever. Almost every job looks at data. So this is a step in that direction of becoming literate in terms of data analysis. And so I encourage you to keep working at it, especially if you're targeting graduate school. And to be honest with you, most of, if not all of you, should be targeting graduate school, because a master's degree is going to be a way to get a job you want in the future. Unless you're going to nursing and, there's a shortage of nurses and they're going to take a bachelor's degree in nursing, right? And some other allied health fields. But you're going to need a master's degree in most fields. I'm not pushing PhD. PhD is a haul. It's a journey. If you want to work at a university, then of course PhD. But in any other field, master's degree will get you far. And stats will be an important part of pretty much every master's degree program, including clinical. So you may just say, I want to do therapy, but you're still going to need to take stats. And you need to understand some of the basics, and this will help you in the future understand some of the basics. And you can drop me a line if you have any questions. Hey, I'm in this program. We're learning about this. I don't understand this concept. I'd be happy to answer, and talk to you about it. So if there's anything you need to know beyond the course, reach out to me. Let me know. I'll talk to you about it. I live, eat, and breathe stats pretty much. So I'm happy to always talk about it. So good luck with the exam. Hope this helps, and see you soon.